gets one great insight, right? So that should have been Newton's. Because just about every other great scientist in the world is great because she or he has had one great insight. But Newton just had them one after another until 1720 when he finally died. I mean, it's unbelievable. So, what did Newton do? All right. Oh, he was born on 2 days. He was born on December the 25th and January the 4th. 10 days apart. 2 birthdays. How did he do it? Any guesses? Okay, think about reformed calendars. Back in 45 BC, Julius Caesar reformed the Roman calendar because they were having March at Christmas. So it wasn't working out too well. So he hired a Greek guy. The Greek guy figured out a new calendar worked pretty good. So from 45 BC up until 1582, Europe had the Julian calendar. And then Pope Gregory said, no, we need a new calendar because this one's out by 10 or 11 days. So they got a new calendar. But then there's Britain. Europe gets a new calendar. The rest of the world gets a new calendar. What does Britain do? No way! So Isaac Newton was born in 1642 or 1643. Britain still hadn't adopted the new calendar. You know when they adopted it? They passed the Calendar Act of 1750. That's when they went on it. That's why Isaac Newton was born on 2 days. Okay, Newton is the guy that we think of when we come to gravity. I just wanted to show you the light bit where he shines light through the prism. So he cut a hole in his blind, let the light shine through it, put it through a prism, saw that it broke down into those different colors, and was able, by taking the rays one at a time and putting them through other prisms, to discern that it wasn't the prism that was creating the color, it was an inherent property of the light itself. So a big step forward in identifying what light was. Okay, well, we'll come back to that. In terms of gravity and the apple, Newton said that the force of gravity is inversely proportional to the square of the distance. And with that, he gave us this beautiful law where you can figure out how far away, do all this stuff with it. And it works beautifully. It's just that if you get into the realm of the very, very, very small or the very, 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 very hot, then it doesn't work quite as well, and you've got to go over the relativistic Einsteinian stuff. But for most everything, it works great. And the laws of motion. You've heard that for every attraction, there's an equal and opposite. That's Newton. He's the guy that gave us that. Oh, and the idea that if you get something moving, it's going to stay moving forever unless something stops it. All right. Over on the continent was the other smartest man in the world, Gottfried Leibniz. And Leibniz had a thing about light too, but Leibniz said, it's not, oh, I forgot to tell you. Newton said light travels in little tiny packets called corpuscles. And Leibniz said, no, it doesn't. It travels as waves. So there was this big debate between the two smartest people in the world who lived at exactly the same time. And the other one was over calculus. Newton was so smart that when he was trying to figure out things like gravity and motion, he had to invent a new form of math to do it. So he invented calculus. So he just blows me away. Over on the continent, Leibniz was doing the same thing. But neither knew the other was doing it. Until they both finally found out, and then a most unseemly rivalry happened. Like, you'd think that people whose IQs were 200 would be mature, I'm not kidding, I'm not exaggerating, would be mature enough to work out their problems in a rational and mature manner, right? But no! Leibniz went back and fiddled with his own books to make it like he'd done things sooner, and Newton caused an inquiry to be held by the Royal Society into who invented it, and then Newton added in the comments about what a fraud Leibniz was. So they were both terrible. Anyway, That was their controversy about light. Is it a particle or is it a wave? This brings us to the last man who knew everything, Thomas Young. Yeah, there he is. By the time that guy was 14 years old, he was speaking 12 languages. And I mean, we're not talking easy stuff. We're talking about ancient Urartu and Hebrew and stuff like that. Young was really smart. Young came up with an experiment. There's one of the most famous in science. It's called the double slit experiment. Probably heard of it. Yeah, well, we don't have to go there. Anyway, what you do in a double slit experiment is you take light and you shine it through two slits. And there's this thing behind it, plate, and what you get is an interference pattern. You shine light through these slits, you shine it through two slits, and you get these four patterns. The dim ones are, well, oh yeah, okay, I've got a thing here I can write on the board. Okay, here you're throwing a stone in the water. The ripples are going out. See? When the ripples hit each other, they cause interference patterns. If they hit each other on the crest of a wave, you get a big wave. If they hit each other not on the crest, you get an interference pattern. And that's what Young got. So Young said there's no doubt about it. The only way you can get an interference pattern is if light is in waves. So, okay, great, it's settled. It's a wave, let's move on. This brings us down to 1865 and James Clerk Maxwell, a scientist no one has ever heard of and which I'm going to rectify immediately. Maxwell in 1865 came up with 4 equations that he'd been working on for 9 years. And in them, he proved that electricity, magnetism, and light are all part of the same thing. Before that, they thought electricity and magnetism was separate. What Maxwell said, he said, nope. He said what light is and what electricity and what magnetism is it's electrical and magnetic fields at right angles to each other, propagating their way through space at the speed of light. I'm not arguing. How smart was Maxwell? Where's that scroll? Did you want to tell me something? I'm probably forgetting all sorts of
I was going to bring you the scroll.
Okay. So I thought I'd try to tell you what Maxwell did.
And don't forget, you're a Maxwell.
That's right. Anyway, forgot to mention my middle name's Maxwell. Not that's got anything to do with any of this, but I was going to try to tell you what he did, but we had this scroll made up. This is just some of it. Just some of it. So when Albert Einstein was visiting Cambridge in 1922, his guide said, "Oh, you must feel like you're standing on the shoulders of Newton." He said, "No, I'm standing on the shoulders of Maxwell." So, I could pass that around later if you want, and so that you just get some sort of an appreciation for what that man did. The fact that his name is the same as mine has nothing whatsoever to do with anything. All right, what else? Yeah, and so Maxwell then, it's a wave, right? The other thing Maxwell did on number 22, he was also the first person to comment intelligently about the butterfly effect. He was one of the first persons to investigate control system chaos theory. First person to produce a durable color photograph. And as I said, a pioneer in control theory and cybernetics. Like, amazing guy. So, that's James Clerk Maxwell, the man who once again said that light was a wave. And now we're ready. We're almost up to the 20th century. We're doing well. I got 3/4 of an hour left, and I think I do, don't I, hon? Why are you going like that? Are you all right? You're going like this.
Move it along, you say.
Move it along, baby.
Okay. All right, let's go over to number 24 then. This is neat. I can sit and talk at the same time. It's actually comfortable. All right, I said that I would try to give credit where it's due. There's some people who in scientific history have been left out. Some of them are women, so I'm going to rectify that situation right now. In 1908, that woman whose ancestors were Pilgrim Fathers, her name is Henrietta Swan Leavitt, and in 1908, she was hired at the Harvard University as a group of computers. These women were called computers, just like, you know, from let's show you like Star Trek. There's always saying computer, computer. Anyway, she was a female computer, and they were hired to work on what the men looking through the telescopes discovered. So the men operated the telescopes, the women weren't allowed to. Women weren't allowed to have degrees in science at most universities. They weren't even allowed to attend science at a lot of universities back in those days, just so you know how it was. We're looking at just over 100 years ago, and this is the situation. And that's something I wanted to emphasize. Almost everything I'm telling you tonight and the entire series, they didn't know 100 years ago. Almost everything that we're sitting here knowing tonight, just taking for granted. We know what the stars are made of. We know the universe is expanding. I mean, we traced our whole evolutionary history back to the last universal common ancestor 4.3 billion years ago. We didn't know any of that 100 years ago. None of it. When I graduated from high school, they'd only figured out the genetic code 7 years before. So a lot has happened in the last time. So here's these women, they're at Harvard, the men are looking up through the telescopes. Henrietta Leavitt is assigned a certain class of stars called Cepheid variables. That's a Cepheid variable. Cepheid variables have bright periods and dim periods. To make a long story short, Henrietta Leavitt figured out all by herself that there was a correspondence between the brightness of the periods and the length of them. And using that, she was able to establish that if you knew the brightness and the period of that star, that you could tell how far away it was. Now just think about that. Up until now, nobody could measure anything more than about 100,000 light years away because they had to triangulate it. But with this, you could go way beyond that. So Henrietta Leavitt then made these Cepheid variable stars into what are called standard candles. You can look at one, and using it, you can figure out where all the other stars around it, how far away they are. And they still use that to calculate, even to this day, the rate at which the universe is expanding. It's expanding at 70 kilometers per second per megaparsec. So you take 70 kilometers per second, and then you have to multiply that by 3.26 billion. And that's how it's expanding. So these guys that I'm going to talk about right now are the ones that figured that out. Okay. So in 1927, so there's Henrietta Leavitt. She gave us the way of figuring out how far things were in the universe. Okay. And now we're briefly going to talk about the other astronomers, and then we'll go to the physicists. But maybe we should look at number 35.
35?
Well, it was going to be Lee Mattray, right?
Oh, okay.
Isn't he 35?
I hope. We'll see.
Okay, this guy's a Belgian priest. Now, I'm going to go back, okay? I've jumped ahead too much, but I just wanted to show you how this got started. In 1927, Lee Mattray is looking at Einstein's equations. I'll tell you about those in a sec. And he realizes, looking at the equations, that the way the equations are set up, I know I already did this once, but again, it's like trying to balance the universe on its tip. He thought to himself, that cannot be. It can't. These equations tell me that the universe is either speeding up or slowing down, that it's either going backwards or forwards, that either at one time everything was in one tiny place, and it's getting bigger. That's what it looks like. So Lemaitre thought to himself, okay, I'm going to call that the primeval atom. It's that point from which everything began. Because if these equations are right, everything is expanding. And if everything's expanding, I'll take it back to the beginning. So I wrote a paper, published it, nobody paid any attention. So nothing much happened at that time. Just keep that in your mind, okay? Okay, now from Henrietta Swan Leavitt, the next person is number 25, Vesto Slipher. Slipher made an amazing discovery in 1915. He was looking at a galaxy, and he saw that it was blue shifted. If I say blue shifted and red shifted, please put up your hand if you think you know what that means. Okay, thank you. Oh, I don't. Go ahead. Sorry. I was just giving you a chance. But hands, blue shifted, red shifted. Okay. Could I have the electromagnetic spectrum, please, my dear? God, sorry, I can't remember what. Oh, there it is. Okay, so thinking back to Maxwell here in the electromagnetic spectrum, here we are with our radio waves down here. They're about the size of a building. And our microwaves, they're a few inches tall. Then the infrared get really small. And by the time you're up here, you're into the width of an atomic radius. So this is the electromagnetic spectrum. This is the part we see. This is Roy G. Biv, right? I love that. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. The only difference between that and that is you can hear this part of the electromagnetic spectrum, but you can't hear this part. But if this part gets into you, it'll ionize your DNA and you'll know something bad has happened. So that's the electromagnetic spectrum. So Vesto Slipher looked at a galaxy and he saw that it was blue shifted. So what does that mean? Well, when a sound wave is coming towards you, okay, see this blue up here? See this red down here? This is where it's red shifted, this is where it's blue shifted. When it's coming at you, these waves get compressed, they get shorter, they become shorter wavelengths, and so they get compressed into the blue zone. That's what you see. If the light gets stretched out, then it goes the other way and it gets stretched into the red zone. And so that's how you can tell. It's so cool. I mean, you turn your telescope on something that's millions of light years away, and you can tell whether it's coming at you or going away by the color of the light that it gives you on the electromagnetic spectrum.
Like a train coming at
It's like a car coming at you. Same,
yeah.
yeah. It's the same thing with sound. Oh, I'm not supposed to respond to that because you're distracted. Bad girl. Anyway, okay, so that's what Slipher discovered. And by a couple of years later, he discovered that everything except one was redshift. So they're all going away except for Andromeda. And he was totally right. We're going to collide with Andromeda in another few million years. It is heading at us, but everything else in the universe is moving away. It's all redshifted. Okay. Okay, and no, that's good enough for them. By the way, he eventually made Henrietta Leavitt department head, and right about that time, a Swedish mathematician, of all people, nominated her for a Nobel Prize. She didn't get it because she was dead. She died of cancer in the meantime. Not a rate. It's a drag. So Henrietta Leavitt, remember that name, please. I love this next guy, Harlow Shapley. He went to elementary school, didn't like it, so he quit. Then he decided he wanted to be a newspaper man. So he had to have high school. So he took 6 years of high school, 1.5 years. And then he was born in Missouri, Nashville, Missouri. Went off to the capital to go to university. He wanted to be a journalist. They didn't offer journalism until the next year. So he said, well, I'm here now. What do you got? He said, well, the first thing is this, and it was archaeology. He said, I can't pronounce that. What's the next one? And he said, astronomy. He said, I'll take that. Slipher ended up as the director of the Harvard Observatory for 32 years. I love it. He also ended up before the House Un-American Activities Committee, and he called them a bunch of brainless primates. Anyhow, he was involved in what is called the Great Debate, and the Great Debate was over this. Again, think about how much we've learned in the meantime. In 1920, the Great Debate was whether the Milky Way was the whole universe or whether it was any bigger, okay? And he took the position that was the whole universe. He was wrong. And Edwin Hubble phoned him up on New Year's Eve in 1925 and said, I just proved that the universe is expanding. And Shapley said, you ruined my universe. Literally wrecked my universe. But anyway, he was a good sport about it. He was right about some things, and that was, he came up with the idea of habitable zones. Heard of those on other planets, right? The idea that other planets have habitable zones that make them fit for life. Well, he came up with the idea, called them water zones. Okay, now the guy with the pipe, Mr. Intellectual, Edwin Hubble. Hubble, there's a Hubble law on account of Henrietta Leavitt's measurements. Hubble was able to finally decide by 1929 and announce to the world Hubble's law, which is that the universe is expanding and that the further you go out, the faster it's expanding.